Hello all and welcome back to this course on computer organization. So we were looking at pipeline hazards and we are now going to focus on the hazard that is shown in instruction 2 and 3 in this particular diagram. Okay, very specifically these are the kind of we need to add some more hardware to basically address this kind of a hazard, okay, where basically the data is written back into the register file only in cycle 5, but it is needed in cycle 3 already, or maybe cycle 4. Cycle 5 we saw what happened, and the shading also indicates that there is no clash or reuse of the resource, so therefore that works correctly by the clock bar solution that we discussed. So what do we do about this problem? Okay, so if you look at it, the contents of the register file, right, are getting written back into the register file only in clock cycle 5, but when I read in clock cycle 3, right, I need that data to be available. Okay, now this is a slightly tricky thing because obviously I don't have the result with me beforehand. Okay, so one solution to this problem, like I told you, right, as I told you even earlier, is to just insert no ops between the two instructions. So the compiler, when it sees such a dependency, it could just say add two no ops in between, and therefore then what will happen, what was cycle 5 earlier will move to what is cycle 3 earlier that needed S8 will move to cycle 5, then your read and write are in different half cycles and you're done. Things will work correctly, right? The other option, okay, of course this is very inefficient because you are wasting 2 clock cycles doing nothing. The other option is to move independent useful instructions forward. Okay, so what is forward? What do you mean by forward? It turns out that data is available on the internal buses before it is actually written back into the register file. There is no need for us to actually wait till clock cycle 5 until the data can be written back into the register file, right? So what we want to do is to simply reuse this data, okay, from the internal buses, right, and just send it to the ALU for processing. Okay, for example, add S8, S4, S3. Clearly, the data is available after clock cycle 3. You read, the ALU gives you the result, and then the subsequent flip-flop is going to capture that, right? So let me again, just get this whole instruction there. Okay, so I have this here. So technically, what you know is that in clock cycle 4, right, you have already sampled the ALU output which has performed S4 plus S5, right, and the output of this flip-flop out here already has that data. It's a 32-bit answer, it's already there. It is exactly the same data which is going to get bypassed through the data memory into that flip-flop, and finally the W version of that data will get, result W will get written back into the register file. Then why not we simply forward this data to the ALU here? That's all we have to do technically, right? And of course this cannot be done directly or obviously, but we can do it a little more carefully, right? Likewise, after the data memory, right, so this takes care of that cycle, data from cycle 5 coming to 3, right, because that's what. Now from cycle 5 to 4 there is another problem, right? So for that all we have to do again is the flip-flop which is capturing the data from after the data memory cycle, right, is again has this same data, right, and therefore you can give it. So this is basically the result W, right, that we are talking about. So if you look at this here, right, what we are talking about is we are talking about the we are talking about this ALU result M right? And we are talking about the ALU result W, which is what was going to get this thing. So these two signals can be used in order to forward the data, and this is what you call register forwarding. Okay. So all you have to do is, if you want to do this register forwarding, you have to check if the source register in the execute stage, because remember, in the execute stage is where the ALU actually has to make a choice. It needs the data. So in the execute stage, it matches the destination register of the instruction in memory or write back. Okay. So this is the key point that I was talking about here. So if you look at this, we are talking about either getting the data from this point in the ALU or from this point in the ALU to the ALU, right? That means either after the execute ALU stage, that flip-flop, right, or after the data memory stage. And that's why what is being said here is, you check if the source register in the execute stage matches the destination register of the instruction in memory or write back stage. If so, you forward the result. What is forward the result? It means don't try to read from registers or something, you just bypass. That means you put a multiplexer there. Okay. So that's why you see that this particular change to the data path is as shown here. What we have basically done is, we have simply added some multiplexers here so that we can choose from the source of the register. Alright. So again, let's get this picture back there so that we can annotate. So right, so let me just reduce this a little bit. Yeah, here we are. So what we have done is, we have added these multiplexers in blue here, which are going to allow you to choose, right, which are going to allow you to choose this sources, register sources for the ALU. So look at this. Earlier there was just this source AE and source BE done in a very simple manner. Now what have we done? We have basically added the multiplexers that control source AE and source BE, right? And what are the inputs to this? Obviously one of the inputs are going to come from the registered read from the register file. Okay. The other inputs are, we are going to choose between two cases. One is either the output of the execution unit, or it is going to be the output of the data memory, right, data memory read operation. So therefore we are looking at ALU result M, right, which is basically one of the inputs, or we are looking at the data from this whole write back phase. So that's what this input is, right? So you have to choose one of these three, either the registered read from the register file, or the registered read from the ALU, or the registered read from the data memory, right? One of these three is what we want to basically choose for this particular for handling this. The select to the multiplexer is what we are going to call as forward AE, forward BE. Okay, so there is some block which is called the hazard unit, which is going to do something. That's a control block that we are adding to choose this hazard unit, right? And that is what we are going to really. So what you see is, the hazard unit is now taking this RS1D, RS2D like this, RS1E, RS2E, okay, and it is going to do some check. Now notice that the other input is actually coming from this destination RDM like this. Okay, what is this RDM? It is basically telling you that the destination register at the memory stage, data memory stage, is what we have to. So why this? Remember, because we had to check that source register in execute stage matches destination register of instruction in memory or write back stage, right? So what are the cases of forwarding? So case 1 is the execute stage. Source 1 register or RS2 register matches the memory stage RD, right? In which case you forward from the memory stage. Okay, so these signals have got, so that's why you are checking the RDM with RS1E and RS2E basically. That's what you are doing here. So in case 1, you are checking RS1E equal to RDM. This is some sort of a Verilog syntax. Then you say the forward AE signal is 10. Okay, again go back here and see this. You are saying forward AE is basically 10. So this is the signal that will get forwarded, which is ALU result M. Okay. So what this is saying is RS1E is equal to RDM, and of course register write M has to be high. Only then you have to do all this, right? Otherwise there is no register write back at all. See, if the register write back if it was not there, then we are not trying to read that new result from that register, right? So that's why you also have to check for register write M, and that's why you see that the this control signal in blue is actually going directly into my hazard unit, and it is also checking this. If you look at this signal, the which is basically the reg write M and reg write W. Okay, so that is what you have here. Else, right, if RS1E equal to RDW, right, that is from the write back stage, it is equal to this and register M, then you say forward AE equal to 0, 1. So therefore 0, 1 is basically going to take this particular output, and that is going to get the result W. Okay, and else forward AE equal to 0, 0. If none of these are met, that means you are trying to forward the data. You are not trying to forward anything, you are just reading from the register as it is. The forward B equations are very similar, except that you have to replace RS1E with RS2E appropriately. Okay. Of course, one important thing you must remember is the RS1E, right, should not be the 0 register, right, because the 0 register cannot be written into. Okay, so that's why you see that there is this and RS1E not equal to 0 also is there. That is, you are saying that the source 1 register is not X0 register. X0, remember, is hard coded to 0. You cannot write back into that. So therefore there is no meaning for that. That answer is always 0, right? So therefore you don't, check for that, and you also make sure you don't allow a write back into that particular case, right? So likewise, there is another hazard due to the load word dependency. So if you look at this, what we are talking about here, you have the sequence of instructions LW S7 40 of S5. So you're doing S5 plus 40, contents of that is going into S7, right? So again, let's maybe take this over here. So we are looking at dependency due to load word. Right. So basically what we are saying is that the S7 is coming out, in the like the 5th cycle, right? 1, 2, 3, 4 and 5, yeah, right? However, right in the 3rd cycle you want that to be the 6. So remember, you are trying to read data from S5 plus 40 and then fetch that into S7. So S7, so this involves a data memory and a register file write back that you are doing. So every single stage in this 5 cycles are shaded to indicate complete usage, right? Nothing is empty. Now you are trying to read this register here, okay, and that is obviously coming from, supposed to be ready only again in the 5th register. Now, of course, just like we did the case of the register forwarding, what we basically need to do is that once you read the data memory output, it is already available here, right? So we have to find a way by which you can feed that back to the ALU, right? The S7 on the other hand can, this is just register forwarding. Data is ready, just give it. This is, there is no conflict because of the clock bar, so there is no issue. So therefore, you need to augment your, register forwarding and do something else about this other problem as well. So you cannot do anything about, getting this data memory thing back to the ALU. Okay, you can do the forwarding here like this somehow, okay, but it is not possible to get the data memory, read the data memory and then make it available to the ALU, right, in the same cycle. So the only way that you can do this, right, is to sort of stall the processor. So you need to basically say, okay, this cycle do nothing. This stalling is inevitable in the pipeline processor because of such hazards. There is no choice, but you can definitely overcome the problem with a simple stalling unit, and that's exactly what is shown here. We are trying to stall this one cycle and solve the remaining using register forwarding. So the stalling logic is either the source register in the decode stage the same as the destination register in the execute stage, right? So basically what we are saying is, in the decode stage, that is this S7 here, is it the same as the destination register in the execute stage? So really that is what we want to do, and is the instruction in the execute stage an LW? So okay, why is load word such a problem? So another data hazard specifically arises due to the load word dependency. Okay, so let's take this image over here as usual. So we are looking at the load word. Earlier, remember what we had was the ALU result gave the data that was needed for the register to consume in the previous cycle. Okay, the ALU result basically is you wanted, for example, S8 to have S4 plus S5 and then use S8 in the next cycle. The ALU result itself had that answer, and therefore if you wanted to move back by just one cycle, it was possible to do this using register forwarding, right? On the other hand, now the problem with the load word, as you can see here, is the S5 plus 40 contents of that needs to get loaded into S7. Now the contents of S7 need to be consumed in the next cycle, but when the register file decoding is happening, right, out here, you are trying to read that data out, right? The ALU still doesn't have the answer, because at that point the ALU only has this answer, right? And therefore there is no way you can just forward that. You have to then wait one more cycle to do a data memory read and then get that answer back into the S7 register. And therefore when you are dealing with this load word, right, you have to be extra careful about this kind of a dependency. On the other hand, once the answer is available from the data memory, right, if the register file decode was just the previous cycle, then you can forward to the ALU directly like this, no problem, right? And of course this kind of a register file read and write happening together is not a problem. They happen in different half cycles, you are saved, right? So you can solve this partially using register forwarding and this different half cycle for register read and write. However, there is nothing that you can do about the immediate next instruction trying to consume the result of the load word. Then the only way that you can solve this problem is to introduce what is known as a stall. you just force the processor to wait one cycle without doing anything, then the result is available from the data memory, then you can forward to the ALU and then you continue the operation, right. So that is how this stall operation is going to work, which means that earlier, right, the operation that actually took 5, 6, so if you look at the previous cycle, in 8 cycles we finished. Now you have no option but to go to the extra 9th cycle, where 1 is a stalled cycle, okay. So basically this is what you want to stall. Now you have to stall everything. So when you say stall, remember, in one you will be doing a register file, in other you will be doing the instruction memory fetch, all of that you have to stall, okay. So what is a stalling logic? It's basically the source register in the decode stage, remember, in cycle 2, right, is the same as the destination register in the execute stage. However, this is not true for all instructions, only if it is a load word instruction. That's why and the instruction has to be a load word, right. So load word stall is RS1D is equal to RDE, or RS2D is equal to RDE, and result source E0, right, is basically, so then you are saying stall F equal to stall D equal to flush E equal to LW stall. So stall the fetch, decode stages and flush the execute stage. So stalling means you are just making it wait. Flushing, then you have to sort of remove that instruction, okay. You have to reset that so that you basically go ahead and redo that operation. So exactly what is happening here, so you have to sort of flush out that instruction, because remember, the instruction that was fetched was decoded and all that stuff, right. So what you are doing now is you have a hazard unit that is controlling the result source, the flush E, stall D and the stall F, corresponding to different stages of the pipeline. F corresponds to fetch, D for decode, E for execute, okay. So you flush out that particular flip-flop, right. So you are basically controlling the clear. The difference between stall and flush is, the flush is controlling the clear of the flip-flop, which means it will just reset the output to 0, right, and the stall on the other hand is controlling the enable of the flip-flop. So you don't allow that flip-flop to read unless it is ready for one cycle, basically that's the idea, okay. So having discussed the data hazards, in the next lecture we will discuss the control hazards, which are equally important for us to solve in this pipelined processor.